The story of John von Neumann's life and work is not only the biography of a brilliant mathematician, but also a lens through which we can witness the evolution of modern science itself. He stood at the intersection of the abstract and the practical, the theoretical and the technological, and in that intersection, he helped to define the modern world. By the middle of the 20th century, his name had become synonymous with mathematical clarity, intellectual versatility, and a vision that saw far beyond the horizon of his time. His identity as a Hungarian-American polymath was not a mere accident of geography or circumstance. It was the reflection of a mind shaped by two worlds and devoted to understanding all worlds. In the United States, von Neumann's genius found both its freedom and its purpose. The post-war period was a time of profound transformation. Nations were rebuilding, new technologies were emerging, and science had become the cornerstone of national power. Von Neumann's work placed him at the heart of this transformation. He was one of the first to understand that the future of knowledge would depend on systems of logic, computation, communication, and organization. To him, mathematics was not confined to the chalkboard. It was a living force that could be harnessed to shape the course of history. One of von Neumann's most enduring contributions was his vision of the digital computer. Although he did not invent the computer itself, his conceptual framework made it possible for computers to evolve beyond mechanical calculators into the powerful programmable machines we know today. In 1945, he authored the first draft of a report on the EDVAC, a document that outlined the fundamental architecture of a stored program computer. This design proposed that both data and instructions could be stored in the same memory, allowing the machine to modify its own operations dynamically. The simplicity and flexibility of this concept became the foundation for virtually all subsequent computer systems. Even now, the architecture that bears his name, the von Neumann architecture, remains the backbone of most modern computing devices. The influence of this innovation cannot be overstated. It transformed the way humans interact with information, paving the way for everything from personal computers to artificial intelligence. Von Neumann's insight revealed not just how machines could compute, but how they could think. He foresaw that computation was not merely arithmetic, it was a form of reasoning, a way of modeling the structure of thought itself. In his later years, he began exploring how the human brain might operate as a computational system, speculating about neural processes and self-replication. These explorations were far ahead of their time and anticipated many developments in modern cognitive science and AI. But von Neumann's intellectual curiosity did not stop at computation. His polymathic instincts led him to confront one of the grandest challenges in science, the problem of life itself. In the early 1950s, he began developing the theory of self-reproducing automata. He imagined a mechanical organism capable of making copies of itself, governed not by mystical forces but by logical and mathematical principles. His model anticipated the idea of genetic replication and, in a sense, predicted the discovery of DNA's structure a few years later. Von Neumann's automata were an attempt to show that the essence of life, reproduction, mutation, and evolution, could be expressed in mathematical terms. His work laid the conceptual foundation for fields like artificial life, cybernetics, and systems biology. In the realm of mathematics, von Neumann continued to produce groundbreaking work. He made essential contributions to functional analysis, ergodic theory, and operator algebras, developing tools that remain indispensable in theoretical physics and probability. His mathematical papers from the 1930s and 1940s are still cited today for their elegance and insight. But what truly distinguished him was his ability to translate abstract mathematics into tools for understanding the real world. For von Neumann, mathematics was not a self-contained art, but a universal language that could describe everything from the behavior of electrons to the choices of human beings. This conviction found its most famous expression in game theory, which he developed with economist Oscar Morgenstern. Game theory sought to describe strategic behavior, how rational actors make decisions in competitive and cooperative settings. Von Neumann's approach was revolutionary because it merged mathematics with the psychology of choice and the economics of competition. The theory's applications would prove vast, influencing economics, political science, evolutionary biology, and military strategy. At its heart lay von Neumann's belief that the same logical structures governing numbers could also govern human behavior. He saw strategy as a kind of mathematics of life, a framework for understanding how order and conflict arise from rational interaction. Von Neumann's influence also extended deeply into national policy and defense strategy. In the post-war era, as the world entered the nuclear age, he became an advisor to the U.S. government, applying his analytical abilities to the pressing problems of deterrence, weapon design, and geopolitical stability. He served on numerous committees, including the Atomic Energy Commission and the Rand Corporation, where his insights shaped early theories of nuclear strategy. Although his advocacy for strong deterrence policies has been criticized by some historians, it reflected his commitment to rational analysis in the face of global uncertainty. For von Neumann, strategy, whether in war, economics, or science, was ultimately a problem of logic. In his later years, von Neumann's polymathy became almost mythic among his peers. Stories circulated about his ability to absorb entire books in a single evening and to recall, word for word, passages from works he had read years before. His memory and mental agility were legendary. Colleagues recalled that he could carry on a conversation about philosophy while simultaneously solving equations in his head. He had an almost intuitive sense for abstraction, a gift that allowed him to leap from one domain of thought to another without losing coherence. To those who worked with him, it often seemed that his mind functioned as a kind of living computer, a metaphor that he himself helped to define. Despite his intellectual dominance, von Neumann's personality was marked by warmth, humor, and charm. He had an infectious enthusiasm for ideas and an unpretentious manner that endeared him to students and colleagues alike. He could joke in 6 languages, tell stories from European folklore, and discuss the fine points of physics or politics with equal ease. His lectures were renowned for their clarity and energy. He had the rare gift of making complex ideas seem simple without ever diluting their substance. Those who studied under him often spoke of the transformative effect of his teaching, a mixture of inspiration, intimidation, and awe. Yet, behind his genial exterior, von Neumann carried the weight of a mind that saw too much. He once remarked that the human brain, though marvelous, was ultimately a machine of limited capacity, trying to grasp an infinite universe. His awareness of both the power and the fragility of human reason gave his work a unique philosophical depth. He understood that logic could illuminate much, but not everything, that uncertainty, whether in quantum mechanics or human affairs, was an inescapable part of existence. This understanding shaped his later reflections on computation and consciousness, where he pondered the boundaries of what machines and minds could know. Von Neumann's illness in the mid-1950s came as a cruel irony to a man whose mind seemed indestructible. When he was diagnosed with cancer, the same intellect that had conquered the most intricate problems of mathematics now turned inward, confronting its own mortality. Even as his health declined, he continued to think, write, and dictate notes from his hospital bed. He spent his final months surrounded by colleagues who visited him not only to offer comfort, but to learn from his still, active mind. His conversations ranged from the technical details of automata theory to the philosophical implications of computation. It was as if he was racing against time to leave behind as much knowledge as possible. He died on February 8, 1957, at the age of 53. His passing sent a shock through the scientific community. Colleagues described it as the loss of an irreplaceable intellect, a mind that had illuminated every field it touched. In the years that followed, his name became a symbol of pure genius, invoked alongside those of Newton, Einstein, and Gödel. But what truly set him apart was not only the depth of his intellect, but its universality. He was the last of a kind, a thinker for whom all knowledge was one, and whose curiosity knew no boundaries. The Hungarian-American identity that defined von Neumann's life reflected a larger synthesis of cultures and ideas. From Hungary, he inherited a deep respect for classical education and rigorous logic. From America, he gained the freedom to apply those ideas to the technological and political realities of the modern world. This fusion allowed him to operate simultaneously as a mathematician, a physicist, an engineer, and a strategist. He embodied the transnational spirit of 20th-century science, where ideas moved freely across borders, transforming global society in the process. The legacy of John von Neumann endures in every computer, every algorithm, and every strategic model that shapes contemporary life. The modern world, driven by data and computation, is in many ways an extension of his thought. The systems he helped to design underpin the technologies that define the 21st century, from artificial intelligence and digital communication to economic modeling and climate simulation. His ideas continue to evolve, finding new expressions in machine learning, quantum computing, and network theory. Wherever logic meets complexity, von Neumann's influence can be felt, but perhaps his most enduring lesson lies not in his inventions, but in his approach to knowledge. He showed that true understanding comes from synthesis, from the ability to see the hidden unity among diverse phenomena. In a time when intellectual life often demands specialization, von Neumann reminds us of the power of integration. His polymathy was not an indulgence in curiosity, it was a method for revealing the interconnectedness of the world. He believed that the laws of mathematics could illuminate the laws of thought, that computation could mirror life, and that reason itself could serve as a bridge between the abstract and the real. His colleagues often struggled to categorize him. Was he a mathematician, a physicist, an economist, a computer scientist, or a philosopher? The answer was always yes, but none of these labels captured the whole. He was, above all, a builder of systems, logical, mechanical, and conceptual. He saw the universe as a grand architecture of information, and he sought to understand its structure through the precise language of mathematics. To study von Neumann's work is to encounter a vision of knowledge that transcends boundaries, a vision in which logic becomes life, and life becomes logic. In the decades since his death, von Neumann's ideas have continued to inspire scientists, philosophers, and engineers. The fields he helped to found have grown beyond anything he could have imagined, yet they still bear the imprint of his thought. Every time a computer processes an algorithm, every time a game theorist models a strategic decision, every time a biologist simulates the behavior of cells, von Neumann's intellectual DNA is at work. His vision of a world governed by mathematical order has become the foundation of our digital civilization. To call John von Neumann a Hungarian-American mathematician and polymath is, in the end, an act of humility in language. No phrase can fully contain the scope of his mind or the breadth of his contributions. He was a man who lived at the boundary of the possible, who believed that reason could unravel the deepest mysteries of existence. He transformed the abstract beauty of mathematics into the practical power of technology, shaping the way humanity thinks, computes, and decides. Even now, his ideas challenge us to think more deeply about what it means to know, to calculate, and to create. His legacy is a reminder that the pursuit of knowledge is not merely an academic endeavor, but a profound expression of what it means to be human. Through his life and work, John von Neumann demonstrated that intelligence is not the mastery of facts, but the art of connection, the ability to weave together the threads of the universe into a coherent whole. As the modern world moves ever further into the realms of artificial intelligence, quantum computation, and complex systems, von Neumann's presence remains palpable. He foresaw a future in which machines would think, information would flow like energy, and human decision-making would be understood as a science. That future is now our present, and his fingerprints are everywhere upon it. His vision continues to guide scientists in their search for deeper understanding, and his name endures as a symbol of what the human mind, at its most luminous, can achieve. In the great tapestry of intellectual history, John von Neumann occupies a place of rare distinction. He was a mathematician whose equations shaped physics, a physicist whose logic built computers, an engineer whose theories defined economies, and a thinker whose curiosity spanned the totality of human knowledge. His life was a testament to the unity of thought, the power of reason, and the infinite potential of the mind to explore, create, and transcend. And so, when we say that John von Neumann was a Hungarian-American mathematician and polymath, we are speaking not just of a man, but of a force, a bridge between eras, a builder of worlds, and a reminder that genius, at its highest form, is not the possession of knowledge but the endless pursuit of it. In the landscape of modern thought, few intellectual revolutions have reshaped human understanding of choice, strategy, and interaction as profoundly as the birth of game theory. At its foundation stands John von Neumann, whose genius transformed scattered ideas about decision-making into a rigorous mathematical science. To speak of von Neumann's role in this transformation is to trace the origins of a theory that forever changed the way individuals, companies, and nations think about competition and cooperation. His work did not merely create a new branch of mathematics, it gave the world a new way to see itself, a framework that described with elegant precision how rational beings behave when their interests intersect. The early 20th century was an age of intellectual upheaval. Mathematics, economics, and physics were being redefined by new concepts that challenged classical certainty. In economics, the dominant theories of the 19th century still relied heavily on assumptions of perfect markets and equilibrium behavior, treating individuals as isolated decision-makers. Yet the world around them was filled with conflict, bargaining, and interdependence. There was no formal language for describing the complex interactions that arise when one person's choice depends on another's. It was into this gap that John von Neumann would bring his revolutionary insight. The seeds of game theory were planted long before the term existed. Mathematicians and economists had long pondered how to analyze games of chance and competition, from gambling tables to market exchanges. But these efforts were scattered and intuitive, lacking a unified structure. Von Neumann's genius was to see that the essence of strategic behavior could be captured through mathematics. He understood that conflict and cooperation, whether in poker, economics, or politics, shared a common logic, a logic that could be formalized, analyzed, and even predicted. Von Neumann's journey toward game theory began in the 1920s, when he was already known in academic circles as a prodigy. Having completed his education in mathematics, chemistry, and philosophy, he was drawn to problems that lay at the borders of disciplines. While teaching and conducting research in Berlin and later at Princeton, he became fascinated by the mathematics of decision-making. His interest was not in games as entertainment, but in their underlying structure. He saw that a game was, at its core, a model of rational conflict, a simplified world where players make choices under conditions of uncertainty, each seeking to maximize their advantage. In 1928, von Neumann published a paper titled Zur Theorie der Gesellschaftsspiel, or On the Theory of Parlor Games. It was a deceptively modest title for what would become one of the most influential papers in modern mathematics. In it, he introduced the concept of the minimax theorem, which became the cornerstone of game theory. The theorem stated that in any zero-sum game, a situation in which one player's gain is exactly another's loss, there exists a rational strategy for both players that ensures an optimal outcome, assuming both act logically and have perfect information about the game's structure. The minimax principle encapsulated the logic of competition: minimize one's maximum possible loss, or equivalently, maximize the minimum gain. This idea seems simple, yet it was revolutionary. Before von Neumann, no one had managed to express such interactions with mathematical precision. His theorem proved that games of pure conflict could be solved logically, that equilibrium existed even in adversarial situations, It provided a mathematical guarantee of balance between opposing rational actors. Von Neumann's insight extended far beyond the parlor games he mentioned in his title. It was a profound statement about the nature of decision and strategy itself. The 1928 paper marked the true birth of game theory. Though the term itself would come later, the essence of the field was already there, the analysis of strategic interaction among rational agents. Von Neumann's approach combined deep abstraction with real-world relevance. He was not content to produce elegant mathematics for its own sake. He sought to capture the logic that underlies all competitive situations, from gambling tables to markets, from military conflicts to human relationships. In the following years, von Neumann refined and expanded his ideas. The world around him was changing rapidly. The Great Depression, rising global tensions, and the approach of another world war made questions of strategy and decision-making more urgent than ever. Economists were struggling to understand unstable markets, political leaders were trying to predict each other's moves, and scientists were redefining the nature of uncertainty. In this atmosphere of intellectual and global turbulence, von Neumann's theory offered a rare sense of order, a way to make sense of choice amid chaos. The next major step came in 1944, when von Neumann joined forces with the Austrian economist Oskar Morgenstern to publish Theory of Games and Economic Behavior. This monumental book transformed game theory from a mathematical curiosity into a full-fledged scientific discipline. The collaboration was itself a reflection of von Neumann's polymathic nature. He brought the precision of mathematics, Morgenstern contributed economic insight. Together, they created a bridge between two worlds that had rarely intersected before. Theory of Games and Economic Behavior began with a bold proposition that economic and social interactions could be understood as games, where individuals and groups act strategically to achieve their goals. The book extended von Neumann's earlier work on zero-sum games to include cooperative and non-zero-sum situations, those in which mutual benefit or shared losses were possible. It introduced the concept of utility, payoffs, and rational choice in a formal way that could be represented through numbers and equations. For the first time, the dynamics of negotiation, competition, and coalition building were given mathematical form. The impact of the book was immediate and far-reaching. Economists, political scientists, and psychologists began to see their fields in a new light. Game theory offered a universal framework for understanding how rational agents behave when their interests conflict or align. It explained not only competition but also cooperation, not only war but also peace. Von Neumann and Morgenstern's vision suggested that human behavior, though often unpredictable in detail, could follow logical patterns that mathematics could uncover. At the heart of von Neumann's framework was the idea of equilibrium, the point at which no player can improve their position by changing strategy, assuming others remain constant. Though the more general concept of Nash equilibrium would later refine this idea, the foundations were already in von Neumann's work. His mathematics demonstrated that even in the most complex interactions, order could emerge naturally from rationality. This concept resonated far beyond mathematics and economics, influencing everything from evolutionary biology to computer science. Von Neumann's role in the development of game theory cannot be overstated. He did not merely contribute to the field, he created its foundations, setting the stage for every later advance. His mathematical rigor gave the theory credibility, while his vision connected it to the real world. In his view, game theory was not just about games or economics, it was about decision-making itself, the logic that governs all intelligent behavior. During the mid-20th century, game theory began to spread across disciplines. Economists used it to study market competition and bargaining, political scientists applied it to diplomacy and voting systems, military strategists used it to analyze deterrence and conflict during the Cold War. Von Neumann's ideas became especially influential in nuclear strategy, where questions of mutual deterrence and rational choice had existential stakes. Concepts such as the balance of power, brinkmanship, and mutually assured destruction were all informed, directly or indirectly, by his mathematical models of strategic interaction. Yet, von Neumann's interest in game theory was never purely military or economic. At a deeper level, he saw it as a study of rationality itself, a way to explore how intelligence behaves in the face of competing objectives. This vision made him one of the first thinkers to bridge human and artificial reasoning. The logic of game theory would later become central to computer science, robotics, and artificial intelligence. In many ways, von Neumann's work anticipated the algorithms that govern modern decision-making systems, from online markets to autonomous machines. His approach to game theory was characterized by a unique combination of abstraction and realism. He could express a game's logic in elegant mathematical terms, yet he never lost sight of the human element. He understood that even the most rational players are constrained by information, uncertainty, and emotion. While his models idealized rationality, he knew that real decision-makers often operate under imperfect knowledge and conflicting goals. This tension between ideal logic and human limitation gave his work a lasting depth and relevance. Von Neumann's creation of game theory also reflected his broader philosophy of science. He believed that mathematics was not an isolated domain, but a universal language capable of describing any system, physical, biological, or social. His work on quantum mechanics had already shown how mathematics could capture the indeterminacy of the physical world. Game theory extended that insight into the social realm, showing that even in the apparent chaos of human conflict, there existed underlying patterns of order. By the late 1940s, von Neumann's reputation as the father of game theory was firmly established, yet he himself saw his work as only the beginning. He continued to refine the mathematical foundations of the theory and to explore its implications for economics, psychology, and computing. His collaboration with the Rand Corporation during and after World War II allowed him to apply his ideas to practical problems of national strategy, resource allocation, and communication systems. These applications demonstrated the versatility of game theory as a tool for both theoretical insight and real-world decision-making. Despite the technical complexity of his work, von Neumann possessed a remarkable ability to explain his ideas in simple, intuitive terms. He often illustrated game theory with examples drawn from everyday life, games of chance, duels, auctions, and negotiations. Through these analogies, he showed that strategic reasoning is a universal aspect of human experience. Whether two nations negotiating a treaty or two children sharing a toy, the underlying logic of interaction remained the same. The intellectual daring of von Neumann's game theory lay not only in its mathematical sophistication, but in its philosophical implications. It suggested that human behavior, long considered unpredictable and emotional, could be studied with the same rigor as the laws of physics. At the same time, it raised profound questions about free will, morality, and the limits of rationality. If decisions could be modeled mathematically, did that mean human choice was deterministic? Could morality itself be reduced to strategic calculation? Von Neumann was aware of these questions, but left them open, recognizing that the theory's power lay not in prescribing behavior, but in describing it. In the decades that followed, game theory would evolve far beyond what von Neumann had imagined, but its foundation remained unmistakably his. His minimax theorem still stands as a cornerstone of the field, and his formal methods continue to define how researchers model strategic interaction. Every new branch of the theory, from cooperative games to evolutionary strategies, from behavioral economics to algorithmic game design, traces its lineage back to von Neumann's early insights. By the time of his death in 1957, John von Neumann had transformed the intellectual landscape. The world of economics, politics, and science would never think the same way about decision-making again. His creation of game theory was not a single discovery, but the birth of a new intellectual paradigm, a way of understanding the world through the interplay of choice and consequence, logic and uncertainty. As Parda draws to a close, we can see that von Neumann's foundation of game theory was more than an academic achievement. It was a profound shift in how humanity perceives itself. Through his mathematics, he showed that every act of choice, every negotiation, every competition carries within it a hidden structure of logic. He revealed that beneath the apparent chaos of conflict lies a deep and elegant order, the geometry of reason itself. When Theory of Games and Economic Behavior appeared in 1944, it marked the culmination of nearly 2 decades of John von Neumann's exploration into the logic of strategic interaction. Yet the publication was not an endpoint. It was the ignition of an intellectual movement that would ripple outward through every domain of modern thought. What began as a study of parlor games soon became the mathematics of survival, negotiation, and choice in an interconnected world. Von Neumann's foundation of game theory transformed not only economics, but the very way humanity conceived of rational behavior. The book's reception was both awe and confusion. Economists were accustomed to equilibrium theories based on aggregated markets, not on the fine-grained logic of individual strategy. Mathematicians marveled at the precision but wondered about its application to human affairs. Yet over time, the audacity of von Neumann's vision became clear. He had provided a framework capable of uniting human motives with mathematical form. For him, economics was not just about money or markets, it was about information, expectations, and interdependence. He saw that every human decision is embedded within a web of others' decisions, a realization that mirrored his understanding of physical systems where each particle's motion affects the rest. The early post-war years became a testing ground for game theory. The Second World War had demonstrated that mathematics could guide military operations, and von Neumann's expertise was sought by the U.S. government. At the Rand Corporation and other research centers, his methods were used to analyze strategic bombing, resource allocation, and later, the perilous logic of nuclear deterrence. His minimax principle found new meaning in this context. Nations sought strategies that would minimize their maximum possible loss, exactly the logic of mutual deterrence that came to dominate the Cold War. Yet von Neumann approached these problems not as a policymaker, but as a scientist of reasoning. To him, a nuclear standoff was an extreme form of a game, governed by the same rules of rational choice that applied to economics or biology. His mathematical rigor stripped away ideology and emotion, revealing the cold symmetry of rational conflict. This analytical clarity both fascinated and frightened his contemporaries. It implied that even the most terrifying human scenarios could be reduced to equations, that survival itself might depend on logic more than morality. Still, von Neumann never lost sight of the broader implications. In his lectures and writings, he often emphasized that game theory was not about promoting conflict, but about understanding interaction. It could illuminate cooperation as much as competition. In his view, rational behavior included not only the pursuit of advantage, but the recognition of mutual dependence. Two players could sometimes achieve better outcomes by working together than by acting alone, a principle that foreshadowed later developments in cooperative games. This insight carried moral as well as mathematical significance, suggesting that logic could, under the right circumstances, favor harmony over discord. The reach of game theory expanded rapidly. In economics, it offered new ways to model markets where participants possess unequal information. In politics, it explained voting behavior and coalition formation. In evolutionary biology, decades after von Neumann's death, his principles helped scientists understand how cooperation and competition shape natural selection. The theory's influence crossed into psychology, sociology, and even philosophy, prompting thinkers to reconsider what it means to act rationally. Each field adapted the mathematical language he created, translating human motives into payoffs, strategies, and equilibria. Von Neumann himself witnessed the early stages of this expansion. At Princeton's Institute for Advanced Study, he encouraged younger scholars to apply mathematical reasoning to real-world problems. He worked closely with economists and engineers, urging them to view their disciplines as interconnected systems. His office became a crossroads of ideas where game theorists, physicists, and computer scientists exchanged insights. Those who met him often recalled the velocity of his mind, how he could leap from a discussion on quantum logic to a conversation about stock markets or the ethics of deterrence without losing coherence. He seemed to live in a realm where all knowledge formed a single continuum, and game theory was his instrument for navigating it. During this period, von Neumann also began to connect game theory to his growing interest in computing. He recognized that strategic reasoning could be mechanized, that machines might one day perform the calculations required for optimal decision-making. His design of the stored, program computer, the architecture that still underlies modern computing, provided the physical means for this vision. A computer, he realized, could simulate not only arithmetic but strategy. In this sense, the development of game theory and digital computation were twin achievements, each enabling the other. Decision-making, whether by humans or machines, followed the same underlying logic. Von Neumann's belief in the unity of knowledge gave game theory a philosophical depth that few mathematical systems possess. For him, it was not merely a tool but a way of seeing the world. Every negotiation, every competition, every exchange of information became an instance of a broader principle, that living beings are constantly engaged in games of choice and consequence. Even the universe, he suggested in private conversations, might be understood as a vast interplay of strategies, an eternal balancing of order and entropy. As the theory gained traction, others began to extend it in directions von Neumann could only glimpse. John Nash's concept of equilibrium, developed in the early 1950s, generalized von Neumann's minimax idea to a wider class of games. Nash's work showed that stable outcomes could exist even when the game was not zero-sum, where cooperation and compromise were possible. Though Nash's name became synonymous with the equilibrium concept, he always acknowledged von Neumann's foundational role. Without the mathematical framework of the 1928 paper and the 1944 book, there would have been no starting point for the equilibrium revolution. Von Neumann welcomed such extensions. He understood that a theory lives only by growing beyond its creator. His curiosity remained boundless, and he continued to explore how game theory could illuminate everything from economic policy to biological systems. He once remarked that life itself could be seen as a process of optimization, organisms adapting their strategies to survive and reproduce. This biological analogy was prophetic decades later. Evolutionary game theorists would describe the dynamics of species in exactly those terms. While his contributions were profound, von Neumann was also aware of the theory's limitations. In private letters, he noted that real human behavior often deviates from pure rationality. Emotions, misinformation, and cultural norms can distort decision-making in ways that mathematics alone cannot capture. Yet rather than viewing this as a flaw, he saw it as an opportunity. By comparing idealized rational behavior with actual outcomes, scientists could measure the forces that shape human choice. Thus, game theory became not just a theory of perfect logic but a tool for studying imperfection. In the years following World War II, the world's great powers increasingly relied on strategic reasoning to manage the precarious balance of peace. Game theory provided the language for this new diplomacy. Concepts like the prisoner's dilemma, mixed strategies, and dominant equilibria entered both academic and popular discourse. Although von Neumann did not invent all these specific models, they grew directly from his groundwork. His mathematics offered a vocabulary for the anxieties of an age in which human survival depended on rational restraint. It was no coincidence that policymakers at Rand and other institutions studied his writings with near religious devotion. For von Neumann, however, the fascination lay less in geopolitics than in the broader principle of predictability within complexity. Whether in war or economics, he believed that uncertainty could be quantified and managed. His work on probability and statistics complemented his game theoretic vision, forming a unified approach to rational analysis under risk. This philosophy of controlled uncertainty pervaded his thinking about everything, from computer design to weather forecasting. To him, the world was not random but patterned, and mathematics was the means of uncovering that pattern. As his career progressed, von Neumann's writings became increasingly reflective. He spoke of mathematics as an extension of human reasoning, an attempt to give form to thought itself. Game theory, in this sense, was more than a science of strategy, it was a mirror of the human mind. Each equation described not only choices and outcomes, but the process of thinking about others' thoughts. A recursive awareness that lay at the heart of intelligence. In predicting an opponent's move, a player must imagine what the opponent imagines about him, creating an infinite loop of consciousness. Von Neumann recognized this paradox early on, long before cognitive scientists formalized it. He saw in this recursive structure a glimpse of the complexity of thought itself. His later work on automata and self-replicating systems further intertwined with game theory. If machines could make decisions, he reasoned, they too would play games, strategic interactions between artificial agents pursuing programmed goals. The boundary between human and mechanical rationality began to blur. Today, when algorithms negotiate prices on stock markets or autonomous vehicles coordinate their movements, they operate on principles that descend directly from von Neumann's vision. The games he once described on paper have come to life in silicon. Von Neumann's illness in the mid-1950s interrupted but did not diminish his intellectual activity. Even as cancer advanced, he continued to advise the government and correspond with colleagues about theoretical questions. Visitors to his hospital room found stacks of papers filled with equations and notes on decision processes. He was still refining his understanding of how rational agents behave under uncertainty, still fascinated by the patterns of choice that define existence. His body weakened, but his mind remained tireless. In those final months, he mused on the future of game theory, predicting that it would merge with the emerging field of information theory to form a science of communication and control. His prediction proved remarkably accurate. After his death in 1957, the expansion of game theory accelerated. Scholars built on his foundations to explore bargaining, repeated games, and evolutionary strategies. Economists used the theory to design markets and auctions. Political scientists used it to model deterrence and cooperation. Psychologists tested it to understand decision biases. Every new branch, every refinement, traced back to von Neumann's core insight, that strategic interaction can be represented, studied, and understood through mathematics. His minimax theorem remained the seed from which the entire intellectual tree grew. Looking back across a century, it is clear that von Neumann did more than lay the foundation for game theory. He redefined the boundaries of reason itself. Before him, strategy was an art guided by intuition. After him, it became a science grounded in logic. His equations transformed the invisible motives of players into measurable variables, turning the uncertainties of choice into analyzable structures. He made it possible to quantify rationality, to map the terrain of decision as precisely as a physicist maps the motion of planets. The legacy of that achievement surrounds us today. From economics to artificial intelligence, from international relations to evolutionary biology, the logic of games permeates modern thought. The strategies of firms competing in global markets, the algorithms that allocate resources online, the negotiations between governments, all operate within frameworks that descend from von Neumann's vision. His mathematics lies beneath the surface of everyday life, shaping outcomes in ways most people never see. And yet, beyond the equations and applications, there remains a deeper resonance in von Neumann's foundation of game theory. It expresses a belief that human behavior, though complex, is intelligible, that reason can illuminate even the tangled web of motives and choices that define society. In a world often driven by emotion and chance, this belief is both hopeful and humbling. Von Neumann showed that beneath the seeming chaos of competition lies an underlying order, a structure that, once understood, reveals the profound coherence of human rationality. His legacy invites reflection on the balance between logic and freedom. If all choices follow mathematical patterns, where does creativity or morality reside? Von Neumann never claimed that mathematics could replace ethics or empathy. Rather, he believed that understanding the logic of conflict was essential to preventing its worst outcomes. To see the game clearly is the first step toward playing it wisely. In that sense, his theory was not merely descriptive but humanitarian. It offered a way to make the world's struggles more transparent and therefore more manageable. In the decades since, game theory has evolved in directions von Neumann might have found both thrilling and perplexing. Behavioral economists have shown that people often act irrationally, defying his assumptions of logical choice. Yet even these discoveries affirm his influence, for they define themselves in relation to his rational model. Artificial intelligence researchers now design algorithms that learn strategies autonomously, effectively bringing to life the theoretical players he once imagined. Each new development confirms that his foundation remains solid, capable of supporting ever more intricate structures of understanding. To say that John von Neumann laid the foundation for game theory in the early 20th century is to recognize one of the great intellectual achievements of the modern age. His ideas bridged mathematics, economics, psychology, and philosophy, creating a language through which human behavior could be analyzed with unprecedented clarity. He did not simply solve problems, he revealed the hidden geometry of choice. The way every decision bends toward equilibrium, every conflict seeks balance, every strategy unfolds within a logical design. His life's work reminds us that reason, when guided by imagination, can unveil the deepest patterns of existence. The foundation he built continues to support new explorations into the nature of intelligence, cooperation, and survival. From the games people play to the systems that govern nations, von Neumann's insight endures as both a mathematical truth and a philosophical beacon. He taught the world that to understand choice is to understand life itself, and that in the grand game of existence, knowledge remains the ultimate strategy. When John von Neumann met Oscar Morgenstern, two intellectual worlds collided and fused into a partnership that would redefine how humanity understood economics, strategy, and human behavior itself. Their collaboration was not an ordinary meeting of minds, but a convergence of disciplines: mathematics and economics, logic and intuition, abstraction and reality. Out of their combined effort emerged Theory of Games and Economic Behavior, a book that became the cornerstone of modern game theory and a blueprint for rational decision making in an uncertain world. It is impossible to separate the story of this collaboration from the broader story of 20th century thought, because their work did not merely add to economics, it changed its foundation. The early 1940s were years of turmoil and transformation. The world was at war, and intellectual life was being reshaped by global conflict and displacement. Many European scientists and scholars had fled to the United States to escape the rise of totalitarianism, bringing with them traditions of rigorous thought and a hunger for new beginnings. Among them was Oscar Morgenstern, an Austrian economist who had been deeply influenced by the Viennese school of logical analysis. Morgenstern had been trained in the classic traditions of economics, but was increasingly dissatisfied with their lack of precision. He found that traditional economic theories could not adequately describe situations involving strategic interdependence, where the outcome for one participant depends on the decisions of others. When he arrived in Princeton, he discovered in John von Neumann a mind uniquely suited to solving that problem. Von Neumann was already a legend, renowned for his work in mathematics, physics, and computing. He possessed a rare ability to cross disciplines without losing depth. Morgenstern, by contrast, was an economist grounded in empirical observation, interested in the human dimensions of markets and decisions. Where von Neumann saw patterns and symmetry, Morgenstern saw behavior and uncertainty. Their collaboration was therefore both improbable and inevitable. Each supplied what the other lacked. The fusion of their perspectives gave rise to a new way of thinking about human interaction that neither discipline could have achieved alone. Their partnership began in 1939 when Morgenstern invited von Neumann to discuss a draft paper on economic behavior. The conversation that followed revealed a shared curiosity about how individuals and groups make decisions in competitive environments. Von Neumann, who had already published his 1928 paper on the theory of parlor games, recognized immediately that economics provided a vast and fertile field for the application of his ideas. Morgenstern, in turn, saw in von Neumann's mathematical precision the tool he had been seeking to bring clarity to the murky world of human decision-making. Over the next several years, the two men would meet frequently, debating, calculating, and refining the ideas that would culminate in their monumental book. Their collaboration thrived on contrast. Von Neumann worked with dazzling speed, moving from one problem to another with an almost mechanical efficiency. Morgenstern, meticulous and reflective, often slowed the pace, questioning assumptions and probing the philosophical implications of their work. This dynamic tension gave their joint project its depth. Von Neumann provided the architecture, Morgenstern furnished the human context. Together they built a theory that was both mathematically rigorous and psychologically insightful. At the heart of their work lay a simple yet profound question: how can one describe rational behavior when outcomes depend not on nature alone, but on the actions of others? Classical economics had treated the individual as isolated, facing impersonal market forces. Von Neumann and Morgenstern introduced a new realism by acknowledging that economic actors constantly interact, anticipate, and respond to each other. In their framework, the economy became a web of games, structured situations in which players choose strategies, seek payoffs, and adjust to the strategies of others. This shift represented a fundamental transformation in economic thought. No longer was the market a static mechanism governed by invisible hands. It became a dynamic arena of strategic interplay. The economist's task was not merely to measure supply and demand, but to analyze the logic of decision and anticipation. This approach reflected von Neumann's mathematical background, which favored models of interdependence over equilibrium, and Morgenstern's philosophical interest in the psychology of choice. The result was a theory that blended mathematics with an acute awareness of human motives. The collaboration also reflected their personal histories. Both men were products of Central European intellectual culture, a milieu that valued rigor, abstraction, and the search for universal principles. They shared a belief that the social sciences could aspire to the same precision as physics or mathematics, provided they adopted the right language. Game theory, as they conceived it, was that language a bridge between the quantitative and the qualitative, the formal and the human. The process of writing theory of games and economic behavior was intense and meticulous. They worked through every concept repeatedly, ensuring that the mathematics corresponded to real-world logic. Morgenstern later recalled the endless discussions in which von Neumann would transform vague economic notions into sharp formal structures. When Morgenstern described a bargaining situation, von Neumann would translate it into a matrix, assigning payoffs and strategies. What had once been subjective became objective, measurable, and reproducible. Their method combined the rigor of geometry with the insight of psychology. The book that emerged in 1944 was unlike anything that had come before. It was vast, dense, and audacious in scope. Its opening chapters established the axiomatic foundations of rational behavior, defining utility, strategy, and equilibrium with mathematical precision. The later sections extended these principles to economics, proposing that markets, negotiations, and even entire economies could be understood as systems of strategic games. Von Neumann's earlier minimax theorem provided the logical bedrock, while Morgenstern's economic insights gave it life and relevance. Together, they created a unified vision of human behavior that encompassed competition, cooperation, and uncertainty. Their theory challenged the orthodoxies of economics. Traditional models had relied on assumptions of perfect competition and market equilibrium, treating actors as passive responders to price signals. Von Neumann and Morgenstern argued that such assumptions ignored the reality of strategic thinking. Real agents, they insisted, do not simply react to prices, they anticipate others' reactions and adjust their strategies accordingly. This recognition introduced psychology into the heart of economics, not as an afterthought, but as a structural feature. Rationality itself became interactive. The intellectual impact of their book was immediate, though not universally understood. Many economists found the mathematics daunting, while mathematicians sometimes dismissed the economic applications as speculative. Yet among the younger generation of thinkers, the book ignited a revolution. It suggested that economics could be made as rigorous as physics, that human behavior could be modeled and predicted through logical structures. The ambition of the project captured the imagination of scholars seeking new methods in an age of scientific optimism. Von Neumann and Morgenstern's collaboration also had a symbolic significance. It represented the merging of two great traditions, the mathematical formalism of the sciences and the humanistic inquiry of the social sciences. In an era when knowledge was becoming increasingly specialized, their partnership reaffirmed the unity of intellectual endeavor. They demonstrated that the boundaries between disciplines are not barriers, but meeting points, where the most creative insights arise. Morgenstern's role in this partnership is often overshadowed by von Neumann's towering reputation, yet his contribution was indispensable. It was he who insisted that the theory remain connected to the realities of human behavior. Without his grounding in economics and his sensitivity to psychological nuance, von Neumann's mathematics might have remained an abstract curiosity. Morgenstern ensured that their work spoke to the dilemmas of real decision-makers, businessmen, politicians, and ordinary individuals faced with strategic choices. His collaboration humanized von Neumann's logic, giving it relevance beyond the blackboard. Von Neumann, in turn, brought to the project a level of mathematical sophistication that transformed it from speculation into science. His ability to formalize concepts, to translate intuition into theorem, made the theory unassailable in its rigor. He viewed the social world as a system of interactions governed by patterns that could, at least in principle, be expressed numerically. His collaboration with Morgenstern allowed him to test that conviction against the messy realities of human behavior, creating a dialogue between ideal logic and lived experience. The resulting synthesis was breathtaking in its generality. Theory of Games and Economic Behavior was not just a treatise on economics, it was a framework for understanding all forms of strategic interaction. It encompassed everything from card games to political alliances, from business negotiations to biological evolution. The book laid out the mathematical foundations for both cooperative and non-cooperative games, for situations where players' interests align and where they conflict. This universality was part of its enduring appeal. By reducing complex social behavior to a set of formal principles, von Neumann and Morgenstern provided a tool for analyzing virtually any system of decision-making. The timing of the book's publication gave it additional resonance. Released in the final year of World War II, it appeared at a moment when the world was desperate to understand the logic of conflict and cooperation. The notion that human struggles could be analyzed scientifically offered a sense of order amid chaos. Military strategists, economists, and policymakers alike found in game theory a way to model their dilemmas with new precision. Though von Neumann and Morgenstern could not have foreseen it fully, their work would become one of the intellectual foundations of post-war planning and policy. Their collaboration also anticipated many later developments in the behavioral sciences, concepts that would become central to psychology and cognitive science. Theory of mind, expectation, bounded rationality were implicit in their analysis of games. They recognized that to predict another's behavior is to imagine their thought process, to enter into a recursive chain of reasoning. I think that you think that I think. This structure of mutual awareness, which later theorists would call reflexivity, was already embedded in their framework. They showed that rationality is not a solitary act but a social one, shaped by the interplay of minds. The partnership between von Neumann and Morgenstern was not without tension. Their temperaments differed sharply. Von Neumann was exuberant, sometimes impatient with details. Morgenstern was methodical and cautious. Yet their respect for each other's strengths sustained the collaboration. Morgenstern later wrote of von Neumann's lightning clarity, while von Neumann acknowledged Morgenstern's indispensable role in grounding his abstractions. Their disagreements were often productive, forcing them to refine their arguments and test their assumptions. The friction between them generated intellectual sparks that illuminated the entire field. By the time the book was published, both men understood that they had created something far greater than a joint paper. It was a new science of interaction. They also knew that their work would take years to be fully appreciated. Indeed, the true impact of their collaboration unfolded slowly, as later generations of scholars built upon their foundation. But even in its earliest reception, Theory of Games and Economic Behavior was recognized as a masterpiece of synthesis, uniting disciplines that had long seemed irreconcilable. For von Neumann, the collaboration with Morgenstern was one of the defining experiences of his career. It allowed him to extend his mathematical philosophy into the realm of human affairs, to demonstrate that the logic of numbers could illuminate the logic of life. For Morgenstern, it was the fulfillment of a lifelong quest to give economics a scientific foundation. Together, they forged a legacy that neither could have achieved alone. Their work marked a turning point not only in economics, but in the entire intellectual history of the 20th century. It exemplified the possibility of interdisciplinary creation, the power of mathematics to reveal hidden structures in social reality. In the decades that followed, their ideas would inspire economists like John Nash, mathematicians like Lloyd Shapley, and countless others who would extend game theory into new realms. But all of these developments rested on the foundation that von Neumann and Morgenstern built together. A foundation born of dialogue, curiosity, and the meeting of two great minds at a critical moment in history. After the publication of Theory of Games and Economic Behavior, the collaboration between John von Neumann and Oscar Morgenstern entered a new phase, not of drafting pages in Princeton offices, but of watching the intellectual world slowly absorb and react to what they had produced. They knew from the moment the proofs left the printer that their work was too large, too unfamiliar, to be immediately understood, yet both men sensed that they had altered the vocabulary of social science forever. The book became a living document, spreading through universities and research institutes like an underground current. Young economists and mathematicians discovered within its dense pages a new language of analysis, a way to speak about choice and interaction with the same precision that physicists used for energy and motion. The world they had written for was changing fast. War had ended, and nations were entering an era of reconstruction, rivalry, and global realignment. In this fragile new order, the logic of conflict and cooperation took on a heightened urgency. Governments sought tools to manage competition without catastrophe. Corporations wanted frameworks to understand strategic markets. Scientists yearned for unified theories that connected human behavior with measurable patterns. In this environment, the von Neumann-Morgenstern collaboration found fertile ground. The two scholars were not merely theoreticians. They became architects of a method that bridged pure thought and practical policy. Von Neumann, with his restless intellect, immediately began extending their ideas to broader applications. At the Rand Corporation, he joined physicists, economists, and psychologists in exploring how strategic reasoning could guide national defense. Morgenstern, meanwhile, continued to refine the economic dimensions of their theory, explaining its relevance to markets, risk, and decision-making under uncertainty. Although they worked separately after 1945, the bond forged through years of collaboration endured. They corresponded frequently, debating extensions of their theory and reflecting on the reception of the book. Each saw in the other an indispensable complement: the mathematician and the economist, logic and life. In these post-war years, game theory evolved into a discipline. Students began to treat theory of games and economic behavior as a starting point rather than a curiosity. At Princeton, Harvard, and Chicago, seminars unpacked its dense chapters line by line. Economists sought to test its implications empirically. Mathematicians worked to generalize its theorems. Von Neumann encouraged these efforts, but reminded his students that the purpose of the theory was not the accumulation of formulae, but the understanding of strategic logic. Morgenstern echoed this sentiment in his lectures, warning against reducing human behavior to mechanical calculation. For both, the beauty of their creation lay in its dual nature, as rigorous mathematics and as a mirror of human reasoning. Their collaboration had been born from a question about rationality, and that question continued to resonate. What does it mean to act rationally when one's outcome depends on another's decision? This inquiry cut across philosophy, economics, and psychology, and the von Neumann-Morgenstern model provided the first systematic attempt to answer it. They had proposed that rational actors assign numerical utilities to outcomes, compare expected payoffs, and choose strategies that maximize their advantage. Yet behind these equations lay a deeper insight: that human behavior is interdependent, that each decision is a response to anticipated responses. This concept of interactive rationality became the cornerstone of modern decision science. Morgenstern's later writings often returned to the philosophical implications of their work. He argued that game theory revealed a paradox at the heart of economics: individuals seek their own benefit, yet their fates are entwined. In striving to maximize personal gain, they must constantly consider the thoughts and intentions of others. This recursive awareness, thinking about what others think, was, in his view, both the source of human conflict and the engine of cooperation. Von Neumann, though less inclined to philosophical reflection, shared the intuition that intelligence itself arises from this interdependence. The mind becomes strategic because it must anticipate the minds of others. Their collaboration had thus illuminated not only markets and games, but consciousness itself. As their ideas spread, new thinkers entered the scene. John Nash, a young mathematician at Princeton, extended the von Neumann-Morgenstern framework beyond zero-sum games. His equilibrium concept generalized their minimax theorem to situations where cooperation or coexistence could emerge. When Nash presented his ideas, both von Neumann and Morgenstern recognized them as natural descendants of their own. They saw that game theory was evolving in the way they had hoped, broadening from a theory of conflict to a theory of interaction in all its forms. This intellectual lineage bound generations together, a chain of insight stretching from the intense conversations of 1939 to the great networked analyses of the modern world. The collaboration also left a personal imprint on both men. For von Neumann, who had long moved effortlessly between mathematics, physics, and computation, the partnership with an economist reaffirmed his conviction that knowledge is one continuum. He often told colleagues that the same mathematical structures appear in seemingly unrelated realms: the equilibrium of a game, the stability of a physical system, the flow of information through a machine. Morgenstern's friendship deepened that belief, showing him that the abstract symmetry of equations could illuminate the messy negotiations of daily life. For Morgenstern, working with von Neumann was an education in audacity. He learned that even the most complex human phenomena could be subjected to formal analysis without losing their essence. The experience transformed him from a cautious theorist into a pioneer of a new science. Their methods influenced not only content but style. The language of theory of games and economic behavior, its careful definitions, its geometric clarity, became a model for interdisciplinary writing. Economists began to emulate its structure, presenting arguments as theorems and proofs. Social scientists adopted its vocabulary: players, strategies, payoffs, equilibria. What began as a collaboration between two men became a shared grammar of modern rationality. The reach of this grammar extended beyond academia. In business, diplomacy, and even everyday language, the notion of playing one's cards, strategic moves, and win-win outcomes acquired new, analytic meaning. The intellectual harmony of their collaboration was occasionally shadowed by the moral questions it raised. Could human values truly be reduced to numbers? Could cooperation be treated as a calculus of self-interest? Critics accused them of promoting a mechanistic view of life. Morgenstern took such critiques seriously and responded that quantification was not dehumanization, it was a means to clarity. By defining the structure of rational behavior, one could better understand its limits and possibilities. Von Neumann, characteristically pragmatic, argued that without formal models, discussions of ethics and policy remained vague and inconsistent. Their exchange on this issue showed the depth of their partnership. It was not merely mathematical but philosophical, a dialogue between precision and conscience. As the 1950s unfolded, game theory's influence reached unexpected domains. Biologists discovered that the strategies described by von Neumann and Morgenstern mirrored the behaviors observed in animal populations. In patterns of competition and cooperation among species, scientists saw analogs of payoff matrices and equilibria. Psychologists began to test human subjects in laboratory games, measuring deviations from predicted rationality. Economists designed experiments to simulate markets as strategic systems. Each new application confirmed the robustness of the von Neumann-Morgenstern foundation. The theory's adaptability testified to the depth of their insight. They had captured a logic that transcended any single field. Morgenstern often reflected on the collaborative process that had produced such enduring results. In interviews, he described long afternoons of debate in Princeton's Fine Hall, where von Neumann would sketch equations on the blackboard faster than anyone could follow. Morgenstern would then translate those equations into economic scenarios, testing whether they reflected real human motives. The interplay between abstraction and intuition, he said, was the essence of their success. Neither could have achieved the theory alone. The mathematician needed the economist to connect logic with life. The economist needed the mathematician to transform intuition into certainty. Von Neumann, for his part, remained modest about their achievement. He viewed game theory as a beginning rather than an end, a foundation for future generations to build upon. In letters to Morgenstern, he speculated about applications that would only later become reality: computer simulations of strategy, automated decision systems, and artificial intelligence. He imagined machines playing games, learning from experience, and optimizing their moves. A vision that foreshadowed the digital age. Morgenstern shared his fascination, though he remained grounded in the social dimension, emphasizing how such tools could aid economic policy and planning. Their divergent emphases reflected the dual nature of their collaboration: theory and application, abstraction and governance. The personal bond between them deepened over the years, sustained by mutual respect and shared intellectual adventure. They corresponded about everything from technical problems to cultural observations. When von Neumann fell ill in the mid-1950s, Morgenstern visited him frequently, bringing books and discussing ongoing research. In those final conversations, they spoke of how game theory had grown beyond them, how new thinkers were taking it in directions neither had predicted. Von Neumann, though weakened, expressed satisfaction that the collaboration had achieved its purpose, to open a door. Morgenstern later wrote that his friend's optimism in those dark days was itself a testament to the power of rational faith, the belief that understanding brings order to even the most uncertain of games. After von Neumann's death in 1957, Morgenstern became the principal custodian of their joint legacy. He continued to write and lecture about game theory, always acknowledging that its true architect had been von Neumann. Yet he also defended the collaborative spirit that had animated their work. He reminded audiences that the theory was not the product of a single mind, but of dialogue, of the meeting of disciplines. In his later memoirs, Morgenstern described their partnership as A conversation that never ended, one that continued in the research of countless students and colleagues. The intellectual consequences of that conversation are still unfolding. Modern economics, political science, and computer technology all bear the imprint of the von Neumann-Morgenstern synthesis. Concepts such as utility maximization, strategic equilibrium, and expected value underpin everything from market design to algorithmic trading. The logic that once described parlor games now governs international negotiations and automated decision systems. Their collaboration thus extended far beyond its original scope. It became a framework for the information age. Yet there is a quieter legacy as well, one that resides in the human dimension of their partnership. In a time of division and upheaval, two refugees from Europe's disintegration came together to create a universal language of reason. Their friendship exemplified the very cooperation their theory described: a mutual recognition of complementary strengths, a negotiation between perspectives, a shared pursuit of truth. They played a game of intellect, and both won. Reflecting on their collaboration decades later, historians have seen in it a model for interdisciplinary creativity. It shows that great innovations often arise not from solitary genius, but from dialogue between different ways of thinking. Von Neumann and Morgenstern combined the precision of mathematics with the empathy of economics, producing insights that neither field alone could reach. Their story reminds us that knowledge grows at the boundaries where languages intersect and ideas collide. The enduring power of their partnership lies in its balance of opposites. Von Neumann sought certainty, Morgenstern sought meaning. One trusted equations, the other trusted experience. Together they forged a synthesis that transcended both. The mathematics of strategy became a philosophy of interaction, a map of human behavior that continues to guide inquiry in disciplines they could scarcely have imagined. Theirs was not just a collaboration of intellects, but of temperaments. A demonstration that diversity of thought can yield harmony of understanding. Today, as scholars use game theory to model everything from climate agreements to evolutionary cooperation, they still trace its lineage to that partnership in Princeton. The equations may have grown more complex, the applications more vast, but the spirit remains unchanged: the belief that rational analysis can uncover the principles governing collective life. Each time a researcher draws a payoff matrix or calculates an equilibrium, a faint echo of von Neumann's logic and Morgenstern's insight resounds. The collaboration between John von Neumann and Oscar Morgenstern stands as one of the defining moments in the history of ideas. It exemplifies how two minds, shaped by different disciplines yet united by curiosity, can create a framework that alters the trajectory of knowledge. Their work transformed economics from a descriptive art into a formal science, infused mathematics with a new relevance to human affairs, and provided modern society with tools to navigate complexity. More profoundly, it offered a vision of rational cooperation in a world prone to conflict, a reminder that understanding, like strategy, is best pursued together. Through their partnership, the abstract became tangible, and the tangible became formal. They showed that behind every human negotiation lies a structure that can be discerned and perhaps even mastered. This insight continues to shape the way we think about markets, politics, and communication. The dialogue they began in the 1940s has not ended. It reverberates in every algorithm that weighs alternatives, in every economist's model of choice, and in every philosopher's meditation on rationality. In the end, the story of their collaboration is the story of a revolution in thought, a revolution that began when an economist seeking clarity met a mathematician seeking connection. From that meeting emerged not merely a book, but a new way of seeing the world, a framework that unites logic and life. Theirs was a partnership built on respect, curiosity, and a shared conviction that the patterns of human behavior, no matter how complex, can be illuminated by reason. Through their work, they gave humanity not just a theory of games, but a deeper understanding of itself. Game theory, the brainchild of John von Neumann, opened a revolutionary path for understanding decision-making. not only in mathematics but across human affairs. At its core, it is the study of how individuals, groups, or institutions make choices when their outcomes depend on the actions of others. In the early to mid-20th century, this idea was nothing short of transformative. It proposed that life, politics, and economics could be viewed as strategic games where participants, rational actors, make moves, anticipate reactions, and seek to achieve the best possible outcomes for themselves. Von Neumann's genius lay in recognizing that the principles guiding parlor games and gambling could also explain far deeper phenomena. The negotiations between nations, the competition between firms, and even the silent coordination between living organisms struggling for survival. To understand the birth of this concept, one must picture the intellectual atmosphere of the 1930s and 1940s. Economics was dominated by theories of equilibrium that assumed independent decision makers responding to market forces, not to each other's choices. Politics and war were studied through history, not mathematics. There was no single framework to connect conflict, cooperation, and rational planning. Von Neumann's insight shattered that limitation. His idea was elegantly simple yet profoundly deep. When multiple decision makers act in a shared environment, each must account for the other's possible strategies. The result is a network of interdependence, a logic of action and reaction that can be expressed through mathematical relationships. In this structure, the world itself becomes a grand strategic game. When von Neumann published his early paper, Theory of Parlor Games, in 1928, he offered the first rigorous mathematical proof of what he called the minimax theorem. It stated that in zero-sum games, those where one player's gain is precisely another's loss, there exists an equilibrium point at which both players can minimize their maximum possible losses. This elegant result gave mathematics a way to analyze strategy as an exact science. But von Neumann saw further. He realized that even beyond games of pure competition, similar principles could describe any situation where rational agents interact. When he later joined forces with economist Oscar Morgenstern, this intuition evolved into the fully fledged structure of game theory, applicable not only to economics but to all realms of decision-making. Their collaboration produced a new way to interpret human choices, one that merged logic with behavior and numbers with psychology. The central idea behind game theory is the interplay of rationality and anticipation. Each player in a game must assume that others are equally intelligent and purposeful, and must therefore predict their possible actions. A choice, in this framework, is never isolated. It is a move made in full awareness of the moves available to others. The brilliance of von Neumann's construction lay in its ability to reduce this psychological complexity into solvable mathematical forms. Matrices of payoffs, sets of strategies, and equilibrium conditions. With these tools, economists could for the first time model markets as systems of strategic interdependence. Governments could analyze conflicts, corporations could plan pricing and competition, and scientists could simulate cooperation in nature. The theory made strategy measurable, turning intuition into calculation. As the theory expanded, it revealed astonishing versatility. In economics, it offered a new lens for understanding monopolies, auctions, and negotiations. In politics, it shed light on deterrence, diplomacy, and coalition building. During the Cold War, military planners used it to frame nuclear strategy, modeling how each side might act to prevent mutual destruction. Even biology found use for its logic. Researchers discovered that the behaviors of animals in competition, fighting, mating, or sharing resources, followed patterns that could be explained as evolutionary games. This universality was no accident. Von Neumann believed that game theory was not just a branch of mathematics, but a universal language of rational interaction, a kind of grammar for decision making that could apply anywhere reasoning beings existed. What made this theory so revolutionary was its ability to blend abstraction with realism. It did not depend on moral judgments or historical context. It focused purely on structure, the logic of choice under constraint. Yet by doing so, it captured something deeply human, the tension between cooperation and competition. Every game in von Neumann's sense is a miniature model of society, where individuals seek personal benefit but must coexist within a network of others doing the same. In this way, game theory mirrored life itself, not as chaos but as a system of interlocking decisions. It revealed that even the most unpredictable behaviors could follow patterns once the underlying incentives were made visible. Von Neumann's ideas did not remain confined to theory. As computing technology advanced, the abstract equations of game theory became practical tools. Simulations and algorithms could now test strategies, predict outcomes, and optimize decisions. The rise of artificial intelligence, in particular, drew directly from the logic he had pioneered. Machine learning models often rely on concepts of equilibrium and reward optimization that trace back to his work. In the 21st century, when computers compete in online markets or negotiate data flows across global networks, they are, in a sense, playing the games von Neumann described decades earlier. His logic has become embedded in the very fabric of digital society. The beauty of game theory lies in its paradoxical blend of simplicity and depth. At first glance, it seems merely a mathematical curiosity, a set of rules for competitive situations. Yet beneath those equations lies a profound philosophical statement about existence. Every interaction, between individuals, nations, or even ideas, can be viewed as a negotiation of outcomes, a dance of strategy shaped by expectation and response. Von Neumann's theory gave this dance a structure, showing that rationality itself can be quantified and studied. It is a reminder that intelligence, whether human or artificial, is defined not only by thought, but by the anticipation of others' thoughts. John von Neumann's contribution to game theory was thus far more than a technical innovation. It was a shift in how humanity conceives of rationality. Before him, reason was viewed as a solitary quality, the property of an individual thinker. After him, it became relational, a web of minds, each reasoning in the presence of others. This transformation continues to shape economics, politics, and science today. Whenever strategists weigh alternatives, whenever negotiators search for compromise, and whenever machines calculate optimal outcomes, they are following the path that von Neumann illuminated. His creation turned the unpredictability of human choice into a field of study, and in doing so, revealed the patterns that lie beneath the seeming chaos of the world. In 1944, a monumental work titled Theory of Games and Economic Behavior emerged from the collaboration of two brilliant minds, John von Neumann and Oscar Morgenstern. This book was not simply an academic publication. It was a landmark moment that transformed the landscape of modern thought. Von Neumann, already a legend in mathematics, joined forces with Morgenstern, an Austrian economist deeply concerned with the limitations of existing economic theories. Together, they built a bridge between pure mathematics and the real-world behavior of individuals and institutions. The result was the formal birth of game theory as a comprehensive framework for understanding strategic decision-making in economics, politics, and beyond. The world at that time was in turmoil. The Second World War had reached its most intense years, and the future of global stability seemed uncertain. Economies were distorted by conflict, alliances were driven by strategy, and survival depended on rational choices in complex situations. Against this backdrop, von Neumann and Morgenstern sought to create a scientific method to analyze decisions in competitive and cooperative environments. They asked a question that would redefine both mathematics and economics: what happens when multiple rational agents, each pursuing their own interests, interact in a shared system? Their answer became one of the most influential theories of the 20th century. The collaboration between von Neumann and Morgenstern was a meeting of two distinct yet complementary intelligences. Von Neumann brought mathematical rigor and an unmatched ability to see structure in chaos. Morgenstern contributed deep insight into economic behavior, human motivation, and institutional dynamics. Together, they created a theory that treated economics not as a static field of supply and demand, but as a dynamic system of interacting strategies. Their work challenged the dominant belief that markets operated through simple equilibrium forces. Instead, they proposed that real-world economics was filled with strategic players, individuals, firms, and governments, whose choices were interdependent. Every action had a reaction, every decision a consequence shaped by others' expectations and responses. In Theory of Games and Economic Behavior, von Neumann and Morgenstern introduced the revolutionary idea that rational behavior could be modeled mathematically. They developed a framework in which all players were assumed to act logically to maximize their own utility or personal gain. By assigning numerical values to preferences and outcomes, they could calculate strategies that led to optimal results. This was a profound leap from the qualitative discussions that had dominated economics. It brought precision and predictability to the study of human behavior, allowing economists to express complex social interactions in the clean language of mathematics. Their collaboration was not merely theoretical, it was methodical and philosophical. They worked through long discussions at Princeton University, where both men had found refuge from war-torn Europe. Morgenstern often presented real economic problems, such as bargaining, competition, and market manipulation, and von Neumann translated them into mathematical language. Through countless drafts and revisions, they refined a structure that could handle both simple and complex interactions. The book they produced was vast, nearly 600 pages of dense argument, proofs, and examples. But it contained within it a new way of seeing the world. One of the key ideas in their work was the concept of equilibrium in strategic games. Building on von Neumann's earlier minimax theorem, they described how players could reach stable outcomes where no one could improve their position by changing strategy alone. This equilibrium principle provided a mathematical foundation for analyzing competition and cooperation alike. Although their original model focused on two-person zero-sum games, the framework was flexible enough to inspire further generalizations. Later thinkers like John Nash would expand these ideas to include situations where all players could benefit, a development that turned game theory into a universal tool for analyzing social and economic behavior. Beyond its mathematical brilliance, Theory of Games and Economic Behavior had a deeper philosophical resonance. It suggested that human interactions, however unpredictable, followed patterns of logic. It implied that even conflict could be studied scientifically, that rationality was not chaos but structure. In a world ravaged by war, this message carried hope. If strategy could be understood, perhaps it could also be controlled. Policymakers and scientists soon recognized the book's importance. Military planners saw its relevance to diplomacy and deterrence. Economists applied it to competition and resource allocation. Psychologists used it to explore decision-making and trust. The collaboration also reshaped the relationship between mathematics and the social sciences. Before von Neumann and Morgenstern, mathematics was largely confined to the physical world, numbers, motion, and geometry. Their work demonstrated that human behavior could be quantified without losing its richness. They showed that economics could achieve the same level of analytical power as physics, provided it embraced formal models. This fusion of disciplines inspired generations of researchers to approach human problems with mathematical precision. It also paved the way for new fields such as decision theory, behavioral economics, and systems analysis. Their partnership was not without challenges. Morgenstern often struggled with von Neumann's abstract methods, while von Neumann sometimes grew impatient with the slow pace of translating intuition into equations. Yet their differences were their greatest strength. The economist grounded the mathematician's imagination in the realities of human behavior, and the mathematician elevated the economist's insights into universal principles. They shared a conviction that true understanding required both logic and experience, both rigor and empathy. Through that balance, they achieved something neither could have accomplished alone. The impact of Theory of Games and Economic Behavior extended far beyond academia. In the years following its publication, it influenced decision making it the highest levels of government and industry. During the Cold War, strategists used its principles to model nuclear deterrence and international negotiation. Businesses adopted its ideas to analyze competition, pricing, and market entry. Even evolutionary biologists found in its framework a means of explaining survival strategies in nature. Every field that dealt with choice and consequence found a reflection of its challenges within von Neumann and Morgenstern's equations. What makes their collaboration truly remarkable is how it transcended its time. They were not merely responding to the crises of their era, they were building tools for the future. Today, the logic they developed continues to shape artificial intelligence, computer algorithms, and economic modeling. Machines now use variations of their theories to make decisions, negotiate outcomes, and predict human behavior. The vision of two men sitting in Princeton, surrounded by notes and blackboards filled with equations, has evolved into a world where those same equations guide automated systems that govern global communication and trade. In the end, the partnership between John von Neumann and Oscar Morgenstern was a fusion of art and science, reason and imagination. It demonstrated that collaboration across disciplines can yield insights that neither field could achieve in isolation. Their joint work gave humanity not just a mathematical tool, but a philosophical mirror, one that reflects the logic and complexity of human existence. Through their efforts, decision-making ceased to be an art of intuition alone. It became a science of strategy, a system of thought that continues to illuminate the patterns of conflict and cooperation that define our world. Game theory did not remain confined to the realm of abstract mathematics or economic philosophy. It grew into one of the most powerful analytical tools of the modern age, revolutionizing fields as diverse as economics, politics, military strategy, and computer science. When John von Neumann first conceived the idea that human decisions could be expressed in mathematical form, he could not have foreseen the vast reach his theory would one day have. Yet, in the decades following his death, his framework for rational interaction began to shape the way societies thought about competition, cooperation, and intelligence itself. It offered not only a language to describe strategic behavior, but a method to predict it, and in doing so, it transformed the foundations of modern thought. In economics, game theory became an indispensable instrument. It changed the way economists understood markets by recognizing that individuals and companies do not act in isolation, but constantly respond to one another. Pricing, production, and investment decisions are strategic moves made within a web of interdependence. Before game theory, economic models relied heavily on the assumption of perfect competition, where each player's actions had no significant influence on the market. Von Neumann's logic destroyed that illusion. He demonstrated that real markets are interactive games where each decision-maker must anticipate the reactions of others. As a result, economists began to analyze markets as strategic systems, studying competition not as a chaotic battle, but as a structured game of choices, incentives, and responses. From auction theory to bargaining models and market design, game theory provided the mathematical backbone for understanding and managing complex economic systems. In the realm of politics, the influence of von Neumann's ideas was equally transformative. Political scientists found in game theory a means to analyze voting behavior, coalition formation, and negotiation. The theory illuminated the subtle balance between self-interest and collective welfare that drives political decision-making. During the Cold War, its applications became particularly striking. The nuclear standoff between the United States and the Soviet Union was a real-world demonstration of a strategic game in which both sides sought to maximize security while minimizing risk. Concepts like deterrence, mutually assured destruction, and brinkmanship were modeled using the principles that von Neumann had laid down. His logic of rational conflict offered leaders a framework to understand how fear, power, and negotiation could coexist in a stable, if fragile, equilibrium. The Cuban Missile Crisis, for instance, can be interpreted as a series of calculated moves and counter moves in a high-stakes strategic game. Policymakers relied on these analytical tools to prevent escalation and preserve balance, illustrating how game theory had moved from the blackboard to the heart of global diplomacy. Military strategists, too, embraced game theory as a scientific way to analyze tactics, logistics, and long-term planning. Von Neumann himself had already been involved in military research during World War II, contributing to the design of early computers and atomic strategies. His understanding of competition and optimization naturally extended to questions of warfare. Game theory offered the military a means to simulate potential conflicts, predict enemy behavior, and test various strategies without the cost of real confrontation. It allowed decision-makers to assess risk systematically, weigh the probabilities of success, and calculate the optimal balance between offense and defense. The Rand Corporation, a think tank where von Neumann's ideas were further developed, became a hub for this kind of analysis. There, mathematicians, economists, and military planners worked together to apply game theory to everything from missile defense systems to information warfare. Through these applications, the theory became an essential part of modern defense strategy. Perhaps the most unexpected evolution of von Neumann's creation occurred in computer science. The logical structure of game theory naturally aligned with the development of computing. As computers grew more powerful, they became capable of simulating complex games with millions of possible outcomes, testing strategies that human minds could only imagine. Von Neumann's own design of the stored, program computer architecture provided the technical foundation for this revolution. The algorithms that govern modern computing, optimization routines, search processes, and artificial intelligence models, are built upon principles first explored in game theory. Machines now play chess, trade stocks, and negotiate contracts using mathematical strategies inspired by von Neumann's insights. Artificial intelligence, in particular, owes a great debt to his vision. Machine learning models often rely on iterative decision-making processes, where algorithms learn to optimize outcomes through competition and cooperation, mirroring the logic of strategic games. In today's interconnected world, the reach of game theory is almost invisible, yet omnipresent. It shapes the algorithms that recommend prices in online markets, the systems that allocate resources in global supply chains, and even the mechanisms that control traffic in cities. Economists use it to design auctions for radio frequencies and energy markets, ensuring efficiency and fairness. Political negotiators rely on it to predict the outcomes of treaties and trade agreements. In cybersecurity, it helps model the constant battle between attackers and defenders, each adjusting their strategies to counter the other. Even in environmental policy, game theory provides tools to analyze cooperation between nations facing global challenges like climate change. It explains why nations sometimes fail to cooperate even when collaboration would benefit all. A tragic scenario known as the prisoner's dilemma, which captures the tension between collective good and individual interest. The influence of game theory extends beyond its practical applications. It also reshaped the way humanity thinks about rationality and interaction. It replaced the notion of isolated rational agents with that of strategic beings embedded in networks of expectation and response. This conceptual shift was profound. It showed that intelligence is not merely about making the best choice in isolation, but about understanding how others make theirs. In a sense, von Neumann revealed that reason itself is relational. It exists not in the mind of a single player, but in the interplay between many. The spread of game theory also transformed education and research. Universities across the world began to incorporate it into economics, political science, and applied mathematics programs. Nobel Prizes were later awarded to scholars who expanded von Neumann's ideas, such as John Nash, John Harsanyi, and Reinhard Selten. Their work deepened the understanding of equilibrium and extended the theory to cooperative situations, behavioral economics, and evolutionary models. Each of these advances traced its lineage back to von Neumann's original insight that competition and cooperation are two sides of the same rational coin. What makes the legacy of game theory extraordinary is its ability to unite the tangible and the abstract. It provides a formal structure for the most complex of human experiences: conflict, trust, negotiation, and choice, without losing their emotional and ethical dimensions. Von Neumann's creation did not eliminate the unpredictability of life. Rather, it gave humanity a framework to understand that unpredictability. It showed that behind every decision lies a pattern, and behind every interaction, a logic that can be studied, modeled, and perhaps mastered. In essence, game theory became a mirror of civilization itself. It reflected how individuals, organizations, and nations pursue their goals within the constraints of others doing the same. It turned the chaos of competition into a system of reasoning, allowing humans to see strategy not as chance but as structure. Through its applications in economics, politics, military science, and technology, game theory continues to shape the modern world, a lasting testament to John von Neumann's vision of a universe governed by intelligence, interaction, and the unending game of reason. John von Neumann's legacy extends far beyond the mathematical theorems and scientific papers he produced during his lifetime. His work continues to shape the intellectual landscape of the modern world, influencing fields as varied as economics, computer science, artificial intelligence, and philosophy. More than a century after his birth, von Neumann's ideas still guide humanity's understanding of logic, strategy, and decision-making. His vision was not confined to a single discipline. It was an all-encompassing view of knowledge as a unified whole. He believed that mathematics could describe not just physical systems, but also the abstract mechanisms of thought, choice, and interaction. In this sense, his legacy is not only scientific, but deeply philosophical, a demonstration that the rational structure of the universe can be mirrored in the rationality of the human mind. At the heart of von Neumann's enduring influence lies game theory, the mathematical framework he pioneered to explain strategic behavior. Its impact is visible everywhere in modern life, from business negotiations to computer algorithms. The logic of competition and cooperation that he formalized now governs decisions in finance, politics, and global relations. Economists use his principles to predict market behavior, while diplomats rely on them to navigate complex international conflicts. In each case, his insight remains the same: rational behavior, when modeled systematically, reveals patterns that can be understood and anticipated. This notion, that the chaos of human decision-making can be described through order, has become one of the most powerful intellectual tools of the modern era. Von Neumann's influence on artificial intelligence is particularly striking. His work laid the groundwork for the very concept of the digital computer. The von Neumann architecture, the design model on which most modern computers are based, was conceived from his belief that machines could replicate aspects of human reasoning. He imagined computers that could process information, store memory, and perform logical operations, a design so effective that it remains the standard in computing today. But even more profound was his belief that machines could learn. He speculated about self-replicating automata, machines capable of reproducing themselves and evolving over time. This early vision foreshadowed the principles of artificial life, neural networks, and machine learning that define today's technological frontier. In every algorithm that adapts and improves, in every simulation that models strategic interaction, there echoes von Neumann's original conception of a rational learning system. His legacy in economics is equally enduring. Before von Neumann, economic theory was largely descriptive, based on assumptions about supply and demand. After him, it became mathematical and predictive. Game theory gave economists a way to model not only markets but the strategic behaviors within them, how companies compete, how consumers respond, and how governments regulate. This mathematical rigor elevated economics to a more exact science and transformed it into one of the central disciplines of the modern social sciences. The Nobel Prizes awarded to economists such as John Nash, Robert Oman, and Thomas Schelling all trace their lineage back to von Neumann's foundation. Each of these thinkers expanded his ideas, applying them to everything from auction design to international diplomacy, demonstrating that his intellectual footprint extended across generations and disciplines. Beyond academia, von Neumann's legacy lives in the systems that govern the modern world. The optimization algorithms that power global trade networks, the strategic models used in military planning, and the AI systems that make split-second decisions, all are built upon principles he helped define. His vision of rational interaction has become the backbone of an interconnected civilization. Yet what makes his legacy even more profound is that it transcends the technical. Von Neumann saw knowledge as a means of understanding the human condition itself. Through mathematics, he sought to uncover the underlying order in both nature and thought. He once remarked that truth is much too complicated to allow anything but approximations, acknowledging that even the most precise models are but glimpses into the complexity of reality. This humility, combined with his brilliance, gave his work a timeless quality. Von Neumann's influence also reaches into philosophy and cognitive science. His exploration of logic and self-reference anticipated questions that would later define studies of consciousness and artificial intelligence. He saw the mind as both a processor of information and a strategic entity capable of reflection and anticipation. His interdisciplinary approach, moving seamlessly between physics, economics, psychology, and mathematics, pioneered a new kind of scientific thinking that refuses to be confined by traditional boundaries. In this way, von Neumann became a symbol of intellectual unity, a reminder that all knowledge is interconnected, and that true innovation often arises at the crossroads between disciplines. Even in ethics and global policy, his legacy endures. The models derived from game theory continue to influence how societies address challenges that require cooperation. Climate change, international trade, and conflict resolution. By demonstrating the logic of both competition and collaboration, von Neumann's work provides a framework for understanding not just how people act, but how they might act better. His insights help explain why nations sometimes fail to cooperate even when it would benefit them, and they offer pathways toward overcoming such dilemmas. Thus, his theories are not merely analytical tools, but philosophical guides for navigating the moral complexities of modern civilization. Von Neumann's brilliance was matched only by his foresight. He anticipated the technological and social transformations that would define the next century. He foresaw the rise of digital computation, the strategic nature of politics, and the interdependence of global systems. In many ways, he predicted the age of algorithms, where decisions, human or machine, are shaped by logical structures similar to those he described. Yet he also warned of the limits of rationality, recognizing that no model could capture the full depth of human behavior. His work thus remains both a triumph of logic and a reminder of the mystery of the human mind. The true measure of von Neumann's legacy is not only in the theories that bear his name, but in the spirit of inquiry he inspired. He embodied the belief that knowledge is a continuous process, a grand game of discovery in which every move opens new possibilities. His life demonstrated that intellect need not be confined by discipline, and that the greatest progress occurs when mathematics meets imagination. Today, as artificial intelligence grows, economies intertwine, and societies become ever more complex, von Neumann's ideas serve as a compass, guiding humanity toward rational understanding amid uncertainty. John von Neumann's work remains a cornerstone of modern thought, a synthesis of logic, strategy, and creativity that continues to shape the world in ways even he could scarcely imagine. His vision transformed not only how people think, but how they build, plan, and dream. Through his mathematical genius and boundless curiosity, he gave humanity a new way to see itself, not as a collection of isolated actors, but as participants in a vast, interconnected game of reason. In that sense, von Neumann's legacy is immortal, living on in every calculation, every decision, and every mind that dares to search for order in the complexity of existence.